Okay, so it is January 26th. We're down to chapter 2, which is the simplest overflow. This is the stuff based on LIFO. This was a well-known sort of underground black hat technique, and LIFO was the guy that wrote it up in Frac magazine, where he actually wrote the first clear tutorial that explained exactly how to do a Stack Overflow, and that's what we're going to cover tonight. This is the original, most popular way to take over a machine. It was the #1 way to take over Windows machines until about maybe 2008. Then Microsoft put in a lot of defenses to stop it, and it declined from like maybe 80% of the attacks down to 5 or 10% of the attacks. And the most popular way as of 2012 or 2014 was dangling pointers, which we'll get to. But this is still the basis of all later attacks. So that's the game here. And the point here is C has this thing called a buffer. You can define, when you save space to store something in C, you have to tell it how big the space is. And if you later put in too much, C doesn't do anything about it. It just lets you overrun the limits and make it crash. So you can do stupid things like this right here. Let's see if this thing is going to run or what. Yeah, just quit complaining. All right. So if I exit, I've got a couple of quit rather. All right, I've got a couple of demonstration programs here. I guess that's big enough. All right, so ch2a.c, let me just cat it. Okay, this program, and I'll make it a little bigger. If I can Shift-Control+, there we are. And this goes up. Let me mess with my screen a little to make this easy to point to and use. All right, so here's the program. The include statements just include some libraries for I/O and manipulate strings. And then I define an array with 5 elements. And in C, they're numbered 0, 1, 2, 3, and 4. So there's an array 0 and an array 4. And then I just print array 5, which doesn't exist. But the way C is, this is the fundamental problem with C. C handles each statement in isolation without any thought. So when it goes down here, it says, well, array is just a pointer that points to the start of this, and the index just tells me how far. So this means start an array and move over 5 bytes and show me that number. And it will just do that without making any attempt to notice that I've gone off the end of the array. Yeah? Yeah.
What did you have to do to modify that, or did you modify that from the book? Because I couldn't get it to compile.
I modified all these from the book. I thought the book was a little too complicated, so I've simplified them, I think. But this, yeah.
Throwing some weird errors.
Yeah, it's possible. But I wrote these. So when I compiled it, I compiled it with this -G, which means it stores symbols with it, which is something you do in development environments to make it easy to debug. But you wouldn't do it in production environment because it makes the code bigger and it makes it easier for attackers to understand your code. So I compiled it. This one compiles that way. In fact, I've got it up here. There's the command that compiles these things, and it works. This was 2A. So I compile. When you compile things, it's GCC for GNU C compiler, and -O tells it where to put the output, which in tradition in Linux is just the name of the program with no extension. In Windows, it would be .exe. And this is the source in C, and that's all you usually do. But if you want to be able to debug it, conveniently, you add -G to add extra symbols. And the purpose of that is, now that I compiled it, I can run it. And it will run and just print out this strange large negative number. Because I defined the array to have 1, 2, 3, 4, 5, and for some reason, the next byte was this large number. And now I'd like to know why. So the way to find out is GNU Debugger. Now the GNU Debugger is the standard, and I've found nothing else to compare with it. There are other things that have more graphical appearance and are much inferior. This one is, however, extremely user hostile. You have to memorize these commands. They're usually 1 or 2 letters, and it's pretty frustrating. And all the online tutorials are 50 pages long. So I learned it is possible to make it simpler. You really only need to learn about 4 or 5 commands here to do what we need to do. That's always what I like. Rather, you don't have to dig something really deep. So you run the GNU Debugger, and then you tell it what to debug, and it's going to be this program, ch2a. This is the executable file, and that's the point of this. If you, for example, have a virus where you have the executable file, but you do not have the source code, that's what you use this thing for. You can analyze binary executables. So that will launch it and print a whole bunch of messages that I don't care about. So now it's loaded into here, but it's not running yet. Now you can run it. When you do it, we'll print this junk out and then exit. So that's not much more than I was doing without the debugger. To get benefit out of the debugger, you usually want to put in breakpoints. Now, if you compiled it with the -G flag, you can do list, which is not normally available to you when you're analyzing binaries, and it will show you the source code. That's what the -G flag did. It connected it to the source code file. So now I can work from C source code, and I can put in a breakpoint, and I think I'll put a breakpoint in before the end, in line 7. I just put a break in line 7, and all that means is when it hits line 7, it will stop. And it will let me examine the state of the computer, and then I use continue to run again. So I break to line 7. Now if I run it, it will print out that number, and instead of ending, it will say you're now at breakpoint 1. And it hasn't stopped, it's still running. Since it's still running, I can look at the value of variables. For example, let me go to my slides. That's reading past the end of an array. And here I can use x/10x array. I don't do this very often because normally you don't have names of variables, so I had to look at the slide. But in this case, I do have the names of the variables because of that -G flag. So I can examine the array, and I can look at 10 binary words starting at the value array. I think do I need an ampersand? Nope, just array, okay. All right, this will let me make my window bigger so that wraps around more nicely. Make my virtual machine bigger and make my window wider. Good, all right. So what you've got here is you're looking at the contents of memory, and this is what you're normally going to do in GNU Debugger. You're going to see 32-bit words, because we're using the 32-bit OS. If you have a 64-bit Kali, go download a 32-bit Kali for the first projects. You can do all this in 64-bit, but you want to start in 32-bit to make it simpler. So this is a 32-bit word and another, and you recognize these numbers, 1, 2, 3, 4, 5. Even for such small numbers as this, by default, C uses 32 bits for every integer. So this is the 32-bit integer 1, and on it goes. And then the next one is just these large other numbers, which are storing things like pointers, beginning routine and such. So now it begins to make sense that I put in 1 through 5, and then which is labeled 0 through 4 in C, and when I print array 5, I print this value, which was put there by some other part of the program, and it's serving a different purpose. So that's why if I continue, it'll exit, and the number it printed out up there, -120 million or whatever it is this mess, interpreted as an integer. The way integers work in C is the positive numbers go from 0 up to about halfway up, 8,000, and things with 8 or 9 or bigger here are negative numbers. So this is a large negative number. Yeah.
64 bits will give you erroneous information.
64 bits will look different. The registers have a different name and they're twice as long. The same principles apply,
I saw that.
but the details are different.
The register started with an R instead of an E.
Exactly.
Yeah.
And they're 64 bits wide, and these will be 64 bits at a time. So the same principles work, but you know, it's a little unfamiliar. Better to start with 32. Yeah. Just all right. So that's a simple thing to do with GDB. So now I can just see what happened. So the next one, I'm going to write past the end of an array, which, as you might imagine, is worse. So let's take a look at this one. I'm going to quit the debugger, and then cat ch2b.c. All right, so now I define an array with 5 elements, and then an integer with I, and then I write 2,000 times 10 in there. Yeah?
I don't understand how you had a value there at all.
Well, it's just a section. See, there's data in RAM beyond what I put there. There's other data it's used to store the value of registers, the indexes of code. Machine language instructions are in RAM. And it could just be random stuff. For example, there was a Ethernet vulnerability called Ether leak, where if you send a ping is too small to fit in an Ethernet network. There's a minimum size to package. It has to be, I think, 48 bytes. So it has to pad it with data. And Windows, up until Windows 95, would just grab random bytes from RAM and use them. And what was in there was whatever the last program left in there. Your RAM is like the hard drive. A program puts junk in there, you close that program, you open another program, and the RAM has leftover junk in there.
Sure.
So RAM always has something in it. Now, if you want to know exactly why this had that value, we will see that. The stuff in the stacked frame serves a purpose that will become a little more clear.
But I mean, the C array is a just like anywhere. There's 0 index, right? So
It does not start with 0.
Good.
No, RAM does not start with zeros. Not unless you put zeros there.
No, the arrays are zero indexed.
It starts with an index of 0, but it does not put zeros in the values. If you do, that's why uninitialized variables, if you don't initialize them, they contain random data. It is weird, but that's just a more form of efficiency. See, C is designed to not waste any cycles doing anything unnecessary. So if you define an array, it doesn't zero it because that would slow you down. It assumes you don't care. That's why it does, when you write to something, it doesn't waste any time checking to see if you've gone too far. It just assumes you know, because the whole thing about C is to be super fast and efficient. That's the plan. Like a car, manual transmission in a car, you want complete control of the computer. You want it to do exactly what you told it to do and not one cycle more. That's what C is for. So if you are a super expert, you can write beautiful, perfect code. But if you make any mistakes, it has no safety net. Yeah?
I think you answered it.
Okay, fair enough. Any others? So this one here is going to write past the end. It's going to write 2,000 times past the end. So let's try that one. This was already compiled. If I do ch2b, of course, it crashes with an error message. The error here is segmentation fault, which means I attempt to access memory outside the memory region that I'm allowed to access for the program, which makes some sense. And we can see that in GDB. If I do this, now I can do list again. And you see I don't get the whole program. By default, it lists 1 to 10. If you want to see the whole thing, you have to give it some more arguments like 1 to 12. There's the whole program in C. And again, I can refer to C-line commands because I compile it with the -G switch. So I can put some breakpoints in here. And the normal thing I would do is put a breakpoint in before and after writing. Let me just see what I planned for in my slides here. Compile and run, open it. All right, just run it and examine the memory. Apparently, I don't even need a breakpoint. I'm surprised at that, but I will follow my script. So I run it. Now I should be, because I don't have to put in a breakpoint because it crashes before it finishes. See, if it finished, it would then not have any of these variables declared anymore, so I couldn't examine them. But if it crashes, that's as good as a breakpoint. It's another kind of breakpoint. So at some point, it crashes in this line here. And if I want to see what's going on, I can examine the array. If I look at the array, I can look at, say, 50 hexadecimal words. That's hexadecimal number 50, by the way, really means 80. And array, and I think it's ampersand array. Yeah, starting at array. So here's 50 words, and the 000A is the number 10 in hexadecimal. So it wrote 10 in the first 5, and then it wrote more and more and more 10s all the way down here. Now some other part of the program actually changed some of these 10s to something else after they were written. So there's FFs in there, but here's a whole bunch of 10s. Way down here, far beyond the array bounds, and that will go on for some large amount, up to 2,000 bytes of A down here, 2,000 words of A, 2,032-bit words. So I've written a whole bunch of A's, and that's what you see. So why does that cause a crash? Why does it matter that you have A's everywhere? Let's look at the registers. This is, I have a general pattern of using GDB. You put in a breakpoint. When you hit a breakpoint, the first thing I always do is info registers before you even think. You want to see what the registers are. Info registers is the full command. IR will work, I space R, which is what you get used to. So this will show me all the registers in the processor. And this is something you're going to look at constantly. Normally when you do a command line and you're copying files, there's a rhythm. You do a command and then you do a DIR or an LS to see what happened. This is your equivalent of that. You do an IR to see what you've done. So here's the registers. E, A, B, C, and D are used for like math and stuff, and I don't really care about them. The ones I usually look at are ESP, EBP, and EIP. Those are the ones that always matter. The EIP tells me what instruction I'm on. I'm at main plus 18 bytes in the main routine. And ESP and EBP tell me the stack. The stack goes from the base to ESP. So it goes from 468 to 448. All right. So I could look at the stack there if I wanted to, and we will want to look at it more in the future. But the point here is there's nothing ridiculous about these registers. I didn't learn a whole lot by looking at them here. So I should look at the assembly code near the instruction pointer to find out what was it doing when it crashed. You can examine, if you x/10x, you'll just see hexadecimal values. If you x10i, you will see instructions, machine language instructions decompiled. So if you're looking, if I look near the EIP, I should find that. And I don't, if I've examined one instruction at EIP, I could do this, x/1i EIP. And then I will see the last instruction that it crashed on. But I'd rather see some context. So I'm going to do 10 instructions starting at -10 bytes. Now it is possible that I'll hit the middle of an instruction by going back, and the first one will be corrupt. But most of the time they'll be okay. And in fact, in this case, it is corrupt because CLD is some weird thing. That was like a random byte left over. But now the rest of this looks right. So here's main plus 30 starting, which is a jump. Then I've got a move and another move and an add and a compare. And this is the one that it crashed. This is the EIP. This little arrow here tells you which one you're on. So it's pretty handy, actually. So what it was doing was moving. Now this is the Intel format of assembly. There are two kinds of assembly, and in one of them you move from here to here, and in the other one you move from here to here. And I always get them mixed up, and all the conventions about capital letters and lowercase letters, nobody obeys them. So after you get used to it, you'll notice that this L and stuff at the end telling you how long the command is only happens in AT&T, but the simplest way to do it is look for a static value. This is the number 10. You cannot write to the number 10. You can only write from the number 10. So this must be the source and that must be the destination. This is putting a 10 in that location. It cannot possibly be putting something into 10. It could have brackets around it and be putting something into location 10, but it can't possibly write anything on top of the static number 10. So that's how I always tell. So this instruction is where it put 10 into a spot in memory. That's just where you expected it to crash in that loop. If you look at my source code, which was up here, it's going to keep doing this array I equals 10. That's what that machine learning instruction does. It puts 10 in a memory location, and sooner or later I will be too big, and that memory location will be out of the accepted bounds, and then it will stop. It's a very simple crash. This is a non-exploitable crash. This is a denial of service condition, but it does not mean you can take over the machine because it's doing something really boring. It's just using up all the RAM until it hits the limit of RAM. There's no obvious way to take over the machine with that kind of crash, and that is the thing about most crashes. Most crashes are what they call non-exploitable. They cause the server to stop, but there is no way to input some other pattern of bytes that would give you something fun like remote code execution. All right, and you can tell that one thing that you would like for an exploitable crash is you would like some of the data you put in to end up in a register. If some of the data you put in went someplace like EIP, that would rock, because then you can control the instruction pointer, you can control the execution. That would be nice, but in this case, none of that happened. EIP just contains a reasonable value, ESP and EBP and all the rest contain reasonable values. The 10s I've been feeding in didn't hit any of them, so I did not get control of any of the registers. All I did was make it crash, so this is not too exciting. All right, and like I mentioned, here's the difference between Intel and AT&T format. In the Intel format, you move this to that. Destination and source first. Here's AT&T. It often has this L or other things at the end to tell you how many bytes are being moved by the instruction. I think this is a long, which is 32 bytes. And then you move from here to there. And there is no consistency whatever in which format is used. You should get used to the fact that all the tools will randomly pick one or the other, and don't freak out too much. All right. Now, and I know I showed the other class Jasmine. I don't remember if I showed you guys Jasmine. But to learn, that's your first project, is running Jasmine. Did I show it to this class? Yeah, good. So you should play with the Jasmine, learn basic assembly there. That's where you'll learn how this works in a nice simple environment. Good. So you got your project 0 and your project 1X are both Jasmine, and you should definitely do them. If you've not done assembly code, that's where you'll learn to do a little simple assembly coding and hopefully get used to it. At first it seems very alien, but you need to learn the basics of it or you can't do exploitation. All right, so the stack is the fundamental thing we're going to take over today. This is the easiest kind of attack and where it all started. The stack is designed specifically to make it possible to call functions and then return. That's why it is last in, first out, which is kind of strange, but that's the way it works. So when you push things on the stack, they go at the top, ESP goes down, piling up, and when you pop them, the last one you put in is the first one that comes out. That's the game there. All right, pop takes things off, push puts things on. Pop, by the way, if I pop this value off the stack, say into EAX, it will go into EAX, and the ESP will increase, and it will not be erased through here. Just like we were talking before, it will be left in RAM as junk, because it's an unnecessary extra step to erase it. The ESP will be down here telling them not to worry about what's up there. But anyway, that's what happens. As you pop, ESP goes down, and the stack gets smaller. As you push, ESP goes up, and the stack gets bigger. All right. So that's the game. EBP typically points to the base of the stack. The stack is in frames. Each subroutine has its own region of stack space, and the EBP points to the base of the current stack frame, which we'll see. All right, so here's what functions are for. The functions are part of structured programming, which is super important. I programmed spaghetti code back in the day before this, and it was awful. You'd have thousands of lines of code would go to everywhere, and trying to change one thing in the middle could break everything else. So it's much better to have little functions that do one job, and you debug them and use call functions to do different things. And so you're very frequently going to interrupt this routine and go call a subroutine. It will do something and then return and pick up where we left off. That's the miracle of the stack. So every time you call a function, the calling routine has to stop processing instructions and not proceed to the next one, save its current state, all the registers and the ESP and EBP and EIP, then transfer control to the function. The function then has to set up its own stack frame with a prologue, where it has its own room on the stack to store temporary local variables. Then it runs its instructions. Then it has to exit, and it has to retrieve the saved state off the stack to resume execution in the calling function. That's the fundamental process that it does every time you call something. So here's an example. I don't know if I coded this one. I think I did. So let's try this one, 2D. Let's quit from this and see if I have 2D. Now I didn't put 2D there. We'll just talk about 2D. There's a more interesting one coming up. So here I'm just going to have a main down here, and the main is going to call that function. That function is going to just declare an array and do nothing and then return. So if you compile it and run it in a debugger, you can then put breakpoints all over the place. Here's what the list looks like inside GDB. You just see all the code. And I'm going to put breakpoints at various statements. So when I run, it's going to start in line 8 and then break at line 9. So I'll be inside main. Now when I'm inside main, it's going to, and I do info registers, I'm going to see ESP and EBP here. The stack goes from 460 to 468. So let's just make a note of that. 460 to 468. And that's when I'm in main. Okay. Now, if I continue and run into the function and then break, now the stack goes from 430 to 450. So that's what I mean by a stack frame. This is in function. So this 20 hexadecimal bytes, 20 hexadecimal words, is the space reserved for function to use while it's in there for temporary storage. And when it's done, it goes back to main that has this setting. So there's a frame created on the stack every time you call a subroutine, and every time you return, that frame is released as stuff is popped off the stack. And it uses EBP and ESP to indicate the bottom and top of the stack. All right, you can examine the stack by just doing X if you like ESP, and you will see this. This is inside the subroutine. The stack goes from 430 to 450. That means if you examine 12 hexadecimal words, it'll give you 30 lines in hex. So this is the first word in the stack. The last word is the one starting at 450, EBP. So this highlighted region is the stack frame for that function. Now the way this works, that is used by the function, and when it returns here. That next word is the stored instruction pointer. That points to the next instruction in main. This is how it returns. When it's done and it hits an exit 0 return statement or just a closing brace in C, it's done with this routine, so it pops stuff to move all this junk off the stack. or changes the ESP directly to say all this is no longer valuable, and it takes this and loads it in the instruction pointer and resumes. And that's the heart of the vulnerability. If we are somehow able to overflow a variable here and change that number, we'll be able to change the EIP. And then we can control the machine. So that's the game. Here's a visual description of this. You've got an array, EBP. This is the local stacked frame in the subroutine, and then it stores the return value, and then it has other values up here. So if I can overflow the array and change this number, when it tries to return to main, it will be returning somewhere else under my control. All right, and that's the game here. If you go back to main, you will resume in line. So I got a few ICA questions, and then we'll do some more of these demos. Yeah, come grab one if you need one. And I'll see if I've got all my cables in. I do, good. Because if I move this cable during it, it kills the sound. Lost a couple videos that way till I learned that. The sound turns into womp, 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 womp.
Bumping the USB?
No, there's some kind of defect in USB. USB is really miserable technology. If this USB is not connected, it fouls up that USB. I've seen so many weird USB bugs. It's just, I'm amazed it ever works. But it never works very well. Anyway, all right. Close that. All right, this is running. So, what is a C data structure like that called? Yeah. All right, guess I'll quit at 30. All right, that's an array in C. All right. By the way, you don't really need to know C before taking this class. All you need to know is a little bit about C, which we're going to cover. We're not going to actually write programs that accomplish anything. We're just going to learn like the 2 or 3 most important errors in C and have simple demonstrations of those errors happening. Real programmers have to spend a lot of time writing stuff that checks for error conditions. And yeah.
Is there a difference between buffer and array?
Buffer is a general term. Array is the specific term for this thing in C. Yeah, buffer is just a temporary, buffer is more the logical description of its purpose, a temporary storage place for data, which could be done, for example, with malloc on the heap, and then it wouldn't be an array, but it would still be a buffer. All right, good. Anyway, all right. So, what's the compiler you use in Linux? I suppose there must be other choices. I've never used anything else, but yeah, you'd think so. Huh. Guess I'll quit at 25. Looks like the answers are in. Yeah, this is the open source one, GCC. I suppose there are others. What else is there? Borland or something?
There's some sort of other structured,
I bet IBM has something.
I can't remember what it is.
Yeah,
I
yeah.
just ran into today.
Yeah, yeah. All right. All right. So what's the GDB command that produces output like that? Think it's big enough to see? I'll quit at 25. All right, that's info registers. These are the registers. Extended stack index, DI, EIP, our favorite. That's part of the registers being listed. So it's info registers. All right. List shows you source code. Info is what shows you the registers. Like I say, there's only about 5 commands to learn, but you do have to learn them. All right. What command shows you things like that? Quitting at 25. All this is X. To examine memory, you're seeing the raw contents of memory in hexadecimal, unprocessed. This is X slash a number X. We'll show you that many words of just raw hex contents. That's what it is. And you can examine any part of memory this way, but it's not terribly enlightening most of the time. But this is the raw contents of memory in hexadecimal. All right. And this one, what command looks like that? All right, quit at 25. All right, and that's that's raw source code. So if you compiled your thing with symbols, with G flag, you can now see the source code and refer to lines of source code, instead of having to refer to lines of assembly code, which is friendlier, of course, especially for beginners. All right, so the stack. The whole purpose of the stack is to efficiently do this process of calling a function and then returning from that function. That's it. So when you call a function, it has to push the arguments onto the stack. The call function has to save the return value so it knows where to come back to. Then it goes into the function. The function has a prologue placed there which prepares for the function, and what it does is adjust ESP and EBP to make a new stack frame. So it takes the EBP and it puts ESP into EBP, so it takes the top of the old stack, the first unused byte, a word rather, and it calls that the start of the new frame, because that's where it should go, and then subtracts some number to move up to make some room, and it calculates that number. It looks at the structure of the subroutine and figures out how much room do I need. So if there's an array with 100 bytes, I'm going to need 100 words here, plus some more. So it calculates how big it's going to, how much room it needs, and saves that room on the stack to make its local frame. That's the game. Then it's going to store local variables on the stack. Variables that are used in the function that are not used in the main program are stored on the stack temporarily so that when the function is over, that memory can be reclaimed and reused. If you fail to let all the memory be reclaimed, that's what's called a memory leak, and many programs have this. Firefox used to have a terrible one, so it would use up all the RAM and crash. Windows 95 and Windows 98 had a terrible one, so every couple of hours you'd have die with the blue screen of death because they would allocate memory for things and forget to let go of it. So the longer you ran it, the more it would just waste memory until it ran out of RAM and crashed. All right, so this is how it looks. If I have a very simple function here, program that just has main down here, and then it's going to call function up there, then the top of the stack is up there, high memory, and the bottom of the stack is down here. When I'm inside the function, it's going to have A and B stored here. Those are stored in main. See, when you call a function, it puts the parameters you need on the stack, A and B, int A and int B, being called as parameters. They're on the stack. Then comes the return value, which is the value of the next instruction. When we're done doing function, we want to go here. So this is what return will point to, printf. Then it has EBP stored, and then you put array up there. This is part of the stack frame for that function. And when it's done, it will move the ESP down here and return, because it's done using that stack frame. And you'll see this in the debugger. All right, so that's the game here. This is 2E. Let me see if I've got 2E in my demo arrangements here. I don't. We'll do 2F, but we're not going to do this one live. All right, so. All right, you compile this thing. All right, you can disassemble main by name, and this will show you the assembly language for the main routine, and that's all there is to it. So it starts with push EBP and move ESP to EBP and push a couple values, 2 and 1. 2 and 1 are going to be the values, A and B. Those are local variables used, so it just stores them locally with push on the stack. Then it's going to call the function name function. You see call, an address, and then function. This is GDB being helpful. It puts the name of the function there, so you don't have to work just from the hex address. Yeah?
Was main plus 3 supposed to be 1 or 2, or is my stack dyslexia going?
Main plus 3, you're right, it's 2 and 1. You're right, they're backwards. Thank you. These are backwards, aren't they? 2. Yeah, 2 goes first and then 1. Thank you. So I should arrange my description here. Good. So this down calls function. Okay. And when it calls the function, it's going to store the EIP of this address on the stack. So it knows to return to. So after this call, we're going to have this number, 804840F, on the stack as the return value. So here's the prologue of the function. It's nice to have a real simple one here. There's not much to it. So here's the function. It enters the function, it pushes EBP, it moves ESP to EBP, and subtracts some from EBP. That's what makes the new stack frame. It stores the old base pointer, so it's there when it's time to return, so it can move the stack frame back where it was. It starts the new stack frame at the first available unused byte, which is ESP, and then it reserves 14 in hexadecimal room for local variables, and now it's ready. It doesn't actually do anything, this function, then it just returns with leave and return. But it does create a stack frame and then return. All right. So now we're going to do this one with the Stack Overflow vulnerability. This is the kind of thing we're going to spend most of the class doing. So here we have main. Main calls a routine, and then it returns. Nothing actually happens in main. You could have a buffer overflow in main, but if you do, it's very hard to understand in the binary because the main routine is handled differently, where you're jumping from the operating system into a program. It's much easier. This is one of the things I learned from Georgia Reedman's book. I kept writing what I thought were simple examples, and they were baffling and complicated in the disassembler until I learned to always write a subroutine and crash in there. Because this step is handled exactly as I've described, but the step from the operating system into user code is more complicated. So we enter main, it calls this. All this does, it has no incoming parameters. It runs gets to take input from the user. Gets will take a string as long as you type it with no boundary checking. It reserves space for 30 bytes, then takes data with no limit, and then prints it. So that's this thing, which is ch2f. Let's run that thing. I've got it here. So if I run ch2f, it now takes data from me. So if I put in some data, it echoes it back, and that's pretty boring. But of course, the interesting thing is if I put in too much. So if I put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've now put in 40 bytes where it's reserved room for 30, 40 characters or reserved room for 30. And now I get a segmentation fault, which means it has overrun the area of memory it expected me to use. And I can find out what happened by using GDB. So I run it on ch2f. And then I run. And then I put in that data again, which I can copy and paste. All right, and now it crashes, and now this is good, clean fun. It stopped, but notice all 4 is there. Now that is the EIP, which is a fun fact, and you can verify that by doing info registers. This is an exploitable overflow because EIP contains 44, 44, 44, 44. Now here's a fun fact in case you don't know. In hexadecimal ASCII, A is 41, B is 42, C is 43, and so on. D is 44. That's why you typically use these letters, because it's very easy to spot them in ASCII and very easy to spot them in hex after you know this. So that I put in 10 Ds, and those Ds ended up in the instructor bucket EIP. So I control the EIP. So now I can take over the machine. I can move the code to run some instruction other than what the programmer intended, which is pretty cool. So let me go back to my slides, and we're going to spend most of the class in every increasing series of projects exploiting conditions like this. All right. So this here I set breakpoints. All right, and we'll set these breakpoints and continue here. All right. So now I've seen that the D's ended up here. Now this looks like an interesting one, so I would like to see in more detail what happened here. So let's do disassemble function. Whoa, did I call it function? I called it echo. It's called return. Let's see what's the name of the stupid thing. Return input. Okay, return. All right, I can disassemble return input, and there's all the code. So I can choose where to put my breakpoint. Now I could use C language to put in the breakpoint, but I might as well do it in binary the way we're going to have to get used to. So here is the cool thing about this is when you call things, it puts the name of the routine there. Whenever you're confronted with something sort of baffling, like assembler, and a lot of it is incomprehensible, just ignore the part you don't understand and look for something easy to understand. And here I have gets and here I have puts. So this is the input from the user and this is the printing out. So I've oriented. So I know that everything is fine until this, and if I put in 40 characters, something bad is going to happen. So the logical thing to do is to put a breakpoint before this and a breakpoint after this. I know if I do the gets, it'll do the print, and when it tries to return, it's going to crash. So a good thing to do would be to a breakpoint here at return input plus 10, so it'll stop before I put in the data, and then a breakpoint, say, down here, plus 22, that would do before it prints it out. Then I'll be able to see the status of memory before and after I put in that input. So that'll work. It doesn't matter exactly where you put them. Yeah.
So the breakpoints using as like a strategy to open up more space on the stack?
No, all the breakpoint does is stop the program executing so you can look at what's going on. So I want to choose interesting points in time to look at it. You could also step through the instruction, one instruction at a time. If you want to, like you did in Heasman, you just go one step, you could do that, but the breakpoints are usually more efficient. So I figure out where the overflow happens, and I look at this memory before and after that. So I'm going to break at return input plus 10, which is star return input plus 10. I think that'll do it, yep. And then, so that puts one right here before it calls the get to take user input, and then I'll put one here at plus 22 before it prints it out, because that's after whatever damage is going to happen has happened. So now I run the program, and I was already in some kind of run. It says start from the beginning. I say sure, start from the beginning. All right, so now it is breaking before it gets user input. So let's try info registers, like say this is always my first move. And I can see that I'm currently in return input plus 10, so I have gone to main, I've called the subroutine, I'm now in the subroutine. The subroutine is where the overflow is going to happen. Here is the stack. That's what I usually look at. EIP tells me where I am. ESP and EBP tell me about the stack. Now I'm just going to record them on this board here. This is handy. So ESP is 43C, and it ends at 460. That is the stack frame. That's the local storage for use inside this subroutine. So if I look at what's on the stack, I can do an x / say 30x of ESP, and I know it's going to go from 43C to 460. So the stack starts here at 43C. Now that's kind of irritating. I think to make it easier, I'm going to start at 430. I'll do it this way. So here's how it works. Might as well get used to it. This is hexadecimal. So C is 12. So, and each one of these is 4 bytes. So this is 3C, this is 40, 44, 48, and this is 4C. Okay? That's how you jump forward. So I want to go up to 60. So this is the word starting at 3C, 4C, 5C. This is the word starting at 60. So that is the stack frame. And by the way, I always do exactly this. View the stack frame and then highlight the stack frame. This is very useful to orient yourself because that is the EIP. So that is my target. If I find a way to change that number, that's the all-important essence of the exploit. So right now, I haven't put anything in. It's just about to read data from me. So let's just put in the data. I'll continue the program. Now it asks for data. Let's put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and see what it does. Okay, now let's look at the stack frame after it took that input. So I do exactly the same thing, and I know I have to end at 460, so that is here. This is the word starting there. So that's the contents of the stack, and here's where the A's are. This is an A and this is an A. There's 4 more and 4 more. By the way, remember this little endian, big endian stuff, just to make sure that you've always got a headache, strings going backwards. So it feeds from right to left, and then from right to left in the next word, and right to left in the next word, which is pretty messed up, but that's the way it is. So this is other things. This is the first A, the second A, that's the third, the next 4, and the next 4. Anyways, those are the A's, and right now, I haven't crashed the program because I only put in 10 A's. So it didn't overrun anything, and this value remains unchanged. So now let's put in the exploit that crashes it. Let's just run from the start again. It's going to complain and warn me that I'm starting over and I might lose my work, but I don't care. So I say yes, the breakpoints will be preserved. So it's going to run to the breakpoint. Now this is before I feed in the data, so I don't really care. I'm just going to continue and feed in the data. Now I'm going to put in that exploit, which is probably in the clipboard maybe. Neat, okay. So that's 10 A's, 10 B's, 10 C's, and 10 D's. Now it didn't crash because I put a breakpoint in. Before it tries to return, it stops to let me see what happened. And I want to examine the stack again. And the stack now looks like this here. So this memory goes to 460, and that means you take the 32-bit words starting at 460. So this is the stack frame. Here's the A's, the 42s are the B's, the 43s are C's, and the 44s are D's. So the first four 44s overwrite this value, which by the way is the stored extended base pointer and would lead to trouble if my program could proceed far enough to die for that reason, but it's never going to get there because this is the stored EIP, and 4444 is not a valid address, and that's why it quits. There's no code there. That's not in the allocated text section where you're allowed to have code, so I give up. I can't execute that instruction. So I can control that. And by the way, you can see that the first 4 Ds didn't matter. It was the next 4 Ds that did it. So if one of the things, we'll be doing a lot of this, but the next step is to make sure you can really target it. So let's just do a more careful attack here. For a more careful attack, run it, start it from the beginning, continue. Now put in the data, and now, there it is, 0123 XX. It's still 40 letters, 40 characters long. I put in 4 Ds, and now I put in 0123. This is how you check to make sure if you've really found how you're hitting the EIP. So now if I do examine the stack, I go down to 460, and now, here's another fun fact. These are just 2 fun things to memorize about ASCII. A is 41, and so on. 0 is 31, and 1 is 31, and 2 is 32. These are really nice things to know. This is how you can avoid being confused by hexadecimal. Just always use capital A's and 0 through 9, and you can easily spot what you're doing. So here is my 0, 1, 2, 3. So in this is my attack code, and those 4 bytes there determine the extended instruction pointer. And of course, they're backwards to make sure we suffer. Yeah?
Can you explain exactly how that is 0, 1, 2, 3 in terms of being backwards?
Yes, because this is written so the most significant thing is on the left. Mm-hmm. It's little endian, so if you actually count the bytes, this is the byte starting at 45C, but this is not the byte 45C. This 45C is the little one. Mm-hmm. This is D, E, F. And strings are stored logically in order in real RAM, but they're interpreted by this display in 32-bit words with the biggest part on the left. That's the thing. That's why it appears backwards here. But anyway, we can now control execution. We can jump to any memory location we want by replacing the 0, 1, 2, and 3 with the bytes we want to put in. Although there are a few complications we'll get to later. All right, the most important one being that since you're injecting into a string variable, you can't put in any null bytes or they'll terminate the string. And there often are other bytes that are misinterpreted by the programs such as tab and return and space. So it turns out to be a little more messed up than just putting in the bytes you want to put in there. There are certain bytes you can't feed in. But in general, that's the point. All right. And so that's the game. You put in 40 characters, you see this. This overwrites EBP and ESP. All right. So we've seen this stuff, the overwritten registers, and that's what it looks like. You have an array of 30. Then you have the EBP and the return value, and you just overwrote all that junk with D's. So you destroyed the ability to return. And by the way, if you were able to return, the stack frame would be all messed up because you messed up the stored EBP. All right, but now we control EIP, and this is the kind of exploit you want, where instead of just running off the end of something like the one that had 2010s, some of the data you put in ends up somewhere really useful, like EIP. Then it's pretty obvious how to take over the machine. All right, so you can feed in a value and jump to that value. In this code, there's nothing much to do, but in the projects, you'll do things like bypass a product key, by just changing the value so it doesn't ask for the product key anymore and things like that. And this is how you cheat at games and crack code and all that jazz. Those are the simplest kind of exploits where you don't have to actually add any code. You just change the order of processing by skipping over some lines or something. The more cool ones are where you inject something and then run it. And in this case, you couldn't do much because you only have 30 bytes of stuff to inject. But if you have more like 300 bytes, then you can actually put executable code in the first 300 bytes and put a pointer at the end that will jump back and run it, and you can run arbitrary code. And that's how arbitrary code execution exploits work. You have to have somewhere to inject stuff, and then some ability to control the EIP to jump there and do it. And stack overflows give you both of those things, as long as the stack is big enough to have enough room for an exploit. And you really can't do much of anything fun with less than about 50 bytes to work with. And most of the time you'd rather have about 300 so you can do like a reverse shell with an IP address and everything. But you can do something with like 30 or 40 bytes, like create a new administrator account or change a password or something. So you can make Python exploit code here that will write this stuff. See, when I want to write to it, if I want to execute the instructions, are typically things like 08, 04, and complicated numbers, and those are not printable characters. So you have to use Python, and sys.out_write is one way to write hexadecimal values here. So let's try this exploit. Let's do it live. So if I go here and disassemble main, it was normally going to return, see here is my messed up stack, where I put in 0, 1, 2, and 3. Now if I continue, this will just crash, because that's not a valid address. Now let's see what it should have been. Back at the stack before I corrupted it, like this one, where I only put in 10 A's, it was this, 8048,444. Okay, let me just write that down. That's the valid EIP, 0804 84 40. That is the stored EIP, which is what should be used if you actually want to run this program without it being broken. Okay, let's see what that is. If you look at my disassembled main, here is that value, 80, 48, 44, 44. It is the next instruction after the call. I call, return input. When it returns, it of course resumes here. Now, if I wanted to make it resume somewhere else, I just have to change this value. Now, this program doesn't really have much in the way of anything to shoot for. Let me just go back in my slides and see what I did before. I think I just, I'm going to go to 4E instead. That's the call to return input. That's one thing. Then this one here, I'm going to 4E. So I guess I'm going to jump back into return input and just run the program again. I said I can do that. All right. So I'm going to, instead of resuming here, I'm going to go back there and make an endless loop where it'll call, return, and call again. It's just so I can see something. So we want to put in this 4E. So I want to feed in these values, 84, 84, 4E. And let's see if it's that way in my case. In my case, it's 44. In my case, it's 3F to call it again. So suppose I want, when I return, to resume here and cut an endless loop. Call, return, call, return, call, return. So I want to put in that. What I usually do is just save this in the clipboard. Now I have to make an exploit that will do that. And the simplest thing is open up another window. So I got my debugger running here. Control N, Shift Control N? Okay, Shift Control N, all right. So let's make an exploit code. I have a general way to do this, nano E1. Okay, shebang, user, bin, pi. There are many ways to do this. A lot of the books you read will, is that right? User, that should work. Okay, a lot of the books you read use inline Perl to do this, which makes it all in one line, but I found it more confusing, and in my earlier classes we're using Python, so I'm a Python addict. So we're gonna use like 4 lines of Python where technically 1 line of inline Perl would do. So now I have to import sys, to write hexadecimal values, I have to import sys and use sys.out_write. So import sys and then sys standard out write. And now I can write stuff. So if I write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to start with this one. That's the one I fed in last time that put 0, 1, 2, 3 in the instruction pointer. The reason why I do it this way is because this will write it
Oh,
without
you
putting
could
an extra
do that.
carriage return at the end. What's that?
Got the last parenthesis too.
Oh, I did, didn't I? Thank you. So that's gonna crash. Good. I gotta close my parentheses. Good. All right. So now I can, it's not, if I try to run this, it's not gonna run, of course. And why is that? What's that?
It's not executable.
It's not executable. If I do ls minus l, I wrote something E, but I didn't make it executable. I have to make it executable shmode plus x E1. Now I can run E1, and it will print out this junk. And the reason why I used that sys.stat outright is because I didn't want an extra carriage return at the end. Okay, so now if I want to work, for example, outside the debugger, I can run this attack, and that would be take E1 and pipe it into the program, which is ch2f. There. And now I get a segmentation fault, which isn't very enlightening, but that's how it works. Now, I could run it inside the debugger with GDB, and there's a couple of ways to refer to files inside the debugger. Let me see which one I put in the slides, because I've learned these at various times. Yeah, run --args. Okay. So what I did is I ran E1 into A1. So I just have a plain text file that contains the attack. Now I debug my program. And then I run it with --args, and the argument is take your data from A1. This is one way to do it. That will feed it in, and now it stops with the instruction pointer containing 0, 1, 2, 3. So I've reproduced the previous one. Now I'd like to actually feed in a valid value there, and that's in my other window, which I should be able to get to this way, there. Here, now I want to go to here. I want to put that value in my Python. And what I typically do here, and I recommend it as the way to avoid getting too confused, is nano your, I always make a series of these, so I copy E1 to E2, because when you do this, you're going to make mistakes and want to go back. Then I nano E2, and you'll do this in all the projects. And now I'm just going to put in a comment, which is the thing I'm shooting for. There. That's the address I want, because it's kind of ugly. I have to take this into bytes and make them backwards. So in this case, I can put them right in line here. Those 4 bytes should be that stuff, which is \x3f, \x84, \x04, \x08. If I haven't fouled it up, that is this backwards. Yeah.
What do you show with the 2 X's?
The \x means raw hexadecimal value.
No, the final 2 X's.
That's just, oh, this is just, you don't need them at all, but it is a good practice when developing exploits to keep the total length of input always the same. So I originally crashed it with 40 bytes, so I'm making sure that all my future attacks have exactly 40 bytes. In this case, it doesn't matter, but in real programs you exploit, sometimes there are multiple crashes. Like 2,000 bytes will crash it, and 2,500 bytes will crash it, but not on the same line. So if you start with 2,500 and then you start changing values, you want to keep the length always the same, just as a good practice. So I made it a habit. So this should do it. This should not crash, but instead run another input. So let's see if that works. And that's E2, so I'm going to run E2 and put it in A2. And then I'm going to GDB this thing and run with arguments and take input from A2, args, and then it prints it and then exits normally. It doesn't crash anymore, more segmentation fault. And if I want to prove that I know what happened here, I can do a disassemble of, say, I don't know what I'd like to do. Let's go to that function, which is I think called return value. Yeah, okay, return input. Let's put a breakpoint here after the gets. That'll probably do. Down here, that plus 22. Break star return plus 22. Now run again. I'm going to run with the same argument. Yeah, run with the arguments. Okay, up here. Okay, that'll run the same attack, but now it's got a breakpoint after the input comes in. So since I've done a breakpoint, I can do info registers, and I can see that my stack is going from 3C to 60, just like before, the ESP to EBP. So I can do X30X ESP and see what my input did. Here's the stack frame down to 60. So there's this, here's the injected stuff, 8048, 0804, 843F. That's what I injected. Okay, and here's those X's, by the way, which don't really matter. Let's change this. So now I can move forward one step at a time. So let's do something we did before. Let's look at what machine language instruction we're on, which is X10I $EIP minus 10. That will give us some orientation. So here's the instructions, and we are here at this put S. We're about to print something out. So let's take one step, step I, and it prints out. Okay, now it jumps into there. I wanted to do a step over. All right, I'm gonna, because I'm calling a subroutine, this is going to be a drag. So I'm just gonna put another break at return plus 30, which is down here at this knob, and then run and continue, because I don't want to jump through the print routine step by step. That's the library code. So now I've made it to this breakpoint. Now let's see where we are now. If I do this, now I have finished printing it out, and now I'm about to leave and return, and my interesting issue is where is it going to go? So now I can do step I, do one step, and that goes to 83A, which is this line. Then I can do another step, and that goes to 3B, which is that line, return. And the question is, where will return go? One more step will tell me. Return now goes back to this line, and if I do this thing again, I now see, now I'm back at the call. Instead of picking up to returning to this line, I return to that line. So in this particular case, it doesn't print out anything different or anything useful, but you can see that I did succeed in altering the code execution to run to a different instruction. And that's the simplest kind of attack. So if that seemed complicated and confusing, don't worry about it. You'll be going over it and over it and over it in the project. You'll be doing these things. And so let me see if I got anything more to put in the slides. Like first time, but I saw that I went through this like in 4 textbooks before I was ready to write this course. You have to go over it until you learn all the tricks. So I got a few of these. Yeah, go ahead.
Can you go back to the
Yeah.
GDB?
Yeah. If I can get out of here. Come on, back to GDB. All right, yeah.
So when you ran the first time when you didn't have any breakpoints, it actually re-input the same line again.
Yes, but unfortunately we had fouled up like EBP and such, but it did come to some kind of end. And it's probably because of the variables I didn't restore, like EBP.
But when you call return input the second time, you would have called gets again.
It should
Gets
have, yeah.
would wait.
But I didn't see that.
Number than you wrote down. So
What's that? I know. Well, these are different than slides because it's a different version of Collier.
You know, you wrote down the number that you wanted to return to the
Yeah.
beginning of the input.
Yeah.
But you copied and pasted a different number.
Did I?
So
Okay.
maybe it went to a different part of the code is why it didn't do it.
That's possible. But actually, if you do step I and follow it, you'll see what happens, and it's not so simple. That's why it's a whole lot. In the projects, I've got nice simple ones where there's like a request for your product key, and you can skip over the comparison, so it takes it whatever it is. It's a little bit more complicated example makes it easier to see. This one here is actually just going to make a mess because I jumped out without properly exiting and called a routine without properly, there was some damage to the stack I didn't fix here. And when I've done this in like CFPs and stuff, you have to be careful to find out what EBP is and not only feed the EIP, but also feed in the correct EBP. Then you can go places, depending on what you're trying to accomplish. Anyway, that's good. Any other questions? Questions are good? All right, so let's just try some of these iClicker questions. And this thing should be running. Run, I say, there we are. All right, so what's the command that will stop execution just after the buffer overflow? Fair enough? Well, I can wait a while. I'll wait till 50. And then we'll talk about it. All right, so the answer is C. Let's see how popular that is.
I see what you did.
More
there.
pretty popular? Good. All right. So the way this works, you always start at main. So it goes into main, it calls return input and goes here. Then it declares an array. Here's where the overflow happens. This is where it takes data from the user. And so the gets is where you can put in too much data. And so breaking at 8 is what will stop right after the overflow. You could, by the way, also break at 9, and that would be okay, but you can't wait any longer because when it tries to leave this and come back, it's going to crash. So you could break at 8 or break at 9, but breaking at 8 is the one that meets the condition here. That will stop right after the overflow, so you can examine the state of memory and see what damage you have done before it crashes. All right, and you're going to get used to that. You're going to have to do that all the time. Break right after the overflow so you can see what you did and adjust your exploit because it takes a lot of trial and error to get these things right. All right. So which one will show me the current contents of ESP, EBP, EIP, and more like that? My favorite command. All right, I think I'll quit at 30. Looks like the answers are pretty much in. All right, that's info registers. What's that? Oh, the battery's dead? Yeah. Okay, let me hold on to it. I'll make a record. You get 1 point for that because you didn't get a fair chance. All right. Anyway, that's info registers. Lets you, when you don't know what else to do info registers. It gives you some idea what's going on. It shows you the state of the current state of the processor. All right. How about this one? If I want to restart this program from the beginning, what do you do? I've run it to some kind of breakpoint and I've gotten tired of investigating that and I want to start over. All right, guess I'll quit at 30. All right, and that's run. Run starts the program from the beginning. Good? All right. All right, which one will execute one line of source code? Didn't mention this, but it'll be mentioned now. That often happens with these iClickers because this is something that almost never matters to us because we usually don't have access to the source code. But I'll quit at 30. All right, and step does a step of source code. Step I does a machine language, assembly language step, which is usually all we can do. But step is the one that would actually do a step of source code, the next line of C, which would be useful if you're debugging code you're writing, but that's not our normal condition. All right. So, which one will give you one line of machine language? Which is equal to one line of assembly. All right. It shouldn't take so long, it's a bad sign. Anyway. There, looks like the answers are in. All right, and that's step I. Hopefully most people got that because I gave it away. Good, all right. But that's all right. And the last one is this thing will not execute. What do I have to do to make it run? I'll quit at 30. Find a piece of paper. All right. and it is Shemode. You have to give it execute permission or it won't run. All right. So I'm going to see who got the most right. Let me stop the recording, which is here.